Mandar un recordatorio, pero es que I don't have the link I was like.
Maybe I can do it. Esto es un coloquio, ¿cierto? Coloquio o seminario. Eso es un seminario. Okay, cool. I was just making sure for the link.
Okay, sure.
Yeah,
I'm using the one you sent me previously.
The one we reutilize every time. Yeah, that's the link we are using right now.
Good.
And it's already recording. Great. So I think we're all set up.
Thank you, Daniel.
No worries.
Me. I'm ready.
Just sending one last reminder to Mingo people.
Yes.
There's a lot of people.
Isn't there? Great.
Nicola Massetti, Lucia Guadagnita, Arciali,
Excellent.
and Gerard.
Good. We have some protocol experts.
Nice.
Online.
They can tell me if I say something wrong.
Aprovecho para recordarles que hay coloquio esta tarde. Es el coloquio de despedida del profesor Patricia Haberle. A todos invitados a ver en el aula.
Sí, o sea, no vamos a tener la teoría de esto y se puede hacer algo. Por el peor de los casos, grabarlo de la forma más burda posible con la cámara, pero existe, me imagino. Sí, voy a ver. Sí, como si no, pensé que me pasé al computador. Tiene una muchísimo mejor cámara que eso. Así que, claro, va a ser el onda sala. Entonces, no vamos a tener esta cámara como para grabar, y no hay mucha opción.
Malte, do you mind if we record you?
No, go ahead. Go ahead.
You want to be on YouTube?
Hey everyone!
You start there, and then you go up. I gathered 15 students to fight for $1 million. No, not gonna go on Mr. Beastman.
I'm here. Let's get started. So, it's my pleasure to introduce you to Malte Brinch, who's our visitor from the Universidad de Valparaiso, and he's going to be telling us all about some proto-clusters. Well, it's a bit of a complicated subject because at the time when we observe them, they're actually groups of galaxies, but they are likely, by the time they get down to redshift 0, to be massive systems like clusters of galaxies. But Malte is going to tell you a lot more detail about that. So a quick career history of Malte. Malte did his PhD at the Danish Technical University, the DTU, and he's currently a postdoc at the Universidad de Valparaiso and working with Edo Ibar. Right? And his research is on galaxies and their environment, and there's this emphasis on these protoclusters and trying to understand how clusters today formed from them. And he uses a whole variety of kinds of data for this analysis, including HST data, Hubble Space Telescope data, Keck, JWST data, ALMA, JCMT, and NOEMA. So all sorts of different types of data that you combine together to get a really kind of multi-analysis of these kinds of objects. So he's also developed a code which is designed to search for protocluster candidates at very high redshift using large surveys. So I think you're going to tell us a bit more about that in your talk. And in his spare time, Malte likes to run and go for walks in the nature. So great place to be in Chile.
Yeah.
And you also like to go to play disc golf. Is that like a kind of frisbee?
It is. Yeah.
Frisbee golf.
Yeah.
Right? Can you do that in Chile?
I think there are some places you can do it, but I think it's more rare in Chile.
Okay, we should set up our own frisbee golf course.
Yes.
I'd like to do that too.
It's really fun. Yeah.
Great. So please welcome Malte. He's going to give us this lovely seminar. Thank you.
Thank you for the introduction. So today I'm going to tell you a bit about a specific protocluster or compact galaxy group that I found. It was initially found with some scuba data and radio data, but we did some ALMA follow-up on it. This talk is sort of in two parts. Firstly, I'm going to give a sort of motivation and introduction to what clusters and protoclusters are. And then later on, I'm going to talk specifically how we can use submillimeter galaxies, so scuba ALMA detected galaxies, as sort of signposts of these protoclusters and galaxy groups. So the idea is, instead of throwing you out with the sharks immediately, I'll teach you how to swim, and then I'll throw you out with the sharks. So we'll start by looking at the sky. So here I have a picture of the sky, completely random, of course. And I want you to look at it and think about what you see. Now, if you look at this long, well, initially you might think, okay, Malte, what am I looking at? It just looks random. There's a bunch of dots of light. They're galaxies, okay. But if you look long enough, what you might see is that it's not random. There is, in fact, collections of galaxies very close together on the sky, close to each other, and they appear to have similar sort of light. Now, this is interesting, and you will not be the first one to have noticed this. This is Hubble, Edwin Hubble, of Hubble of fame, in 1934. So this is a couple of years after we actually discovered that there were other galaxies in the universe than the Milky Way. And what he did is he went out with his 2.54 meter telescope, and he looked, and he started dividing the sky into cells, and he started counting. And what you see here is the distribution of the sky. The small dots are sort of the normal distribution of what you expect, a couple of 50, 100 galaxies. The big ones are excesses, so more than that, and then if they're less, then they're deficient. And you'll notice two things. Well, first you'll see, well, there's nothing here towards the center, and that's because you're looking into the Milky Way disks, so you don't see anything. And this is why it's very deficient. But you can see that if you look away from the disks, there's many places where you have these collections of galaxies that are above what you would expect. And this is one of the first signs of what we call galaxy clusters, observational. So what are galaxy clusters? Well, said in sort of one line, like one sentence, is they're the most massive, virialized, gravitationally bound structures in the universe. And that's a mouthful. So we'll go through some of the properties individually. You see an example of one of them here. This is the Virgo cluster. It rests at 0.0034, so it's very near to us. Very beautiful picture. You can see all the different kinds of galaxies. So what are the properties of these clusters? Well, one, they have many galaxies. This is sort of a simple fact, but it's important to keep in mind, right? So you can have hundreds of galaxies, or in the case of something like Virgo, more than 1,000. What else? They contain many red and dead galaxies. So what does this mean? Red means they have very red colors, and dead means they essentially don't form any stars. Most of the star formation today don't happen in clusters. It happens in field galaxies. So you have these lenticular and elliptical galaxies in the clusters. They're massive and dense. So the structures can have masses accounting for dark matter that is above 10 to the 14. right? So these, again, are massive, but they're also very dense. So not only do you have a lot of galaxies, they're also in a dense environment, which means you can have a lot of interactions and mergers, and you also have the hot gas in the intercluster medium, which can strip gas, for example, through ram pressure stripping as galaxies move through the cluster. So it's a very complex environment. And they're virialized, which means essentially they're dynamically relaxed. So while the internal parts of the structure can interact and move, the overall structure doesn't collapse or expand. Right. So that's sort of some of the general properties of a cluster. Now, this is very interesting. Of course, we want to understand how do these structures form and evolve over time. So from our understanding of cosmology, lambda CDM, what you have is initially these structures grow as primordial density fluctuations, and then you have dark matter, and of course the baryons and the galaxies that form within them grow over time. So you have these dark matter halos that form through, and the galaxies within them form through hierarchical structure formation. So you have small things that grow over time to, in the end, become these large clusters. This is emphasized by something like this. This is a merger tree of the dark matter halos over time after a series of mergers. So you start up here, early universe, and then you go down and you can see over time they will merge and grow until at the end they form the final cluster. Now, because you have these dense environments and all these interactions and tidal tails and stripping and all this as part of the, and also part of the formation process, this virialization, what happens is it's very difficult to say something about the evolution of these clusters just from looking at their how they are in the present day, or as we observe them. So what we have to do is we have to go to the past, essentially higher redshift, go to the past and look and see their progenitors, so-called protoclusters, to understand how they form and evolve over time. Right? So we want a series of snapshots across different redshifts to say, okay, what is the sort of story of the evolution of the clusters? Now, if we could see dark matter, this would be fairly easy, right? You would put on your dark matter goggles and you would go look and you would say, oh, look, this redshift or at this time, there's the concentration of dark matter. And then you could just follow those concentrations at different points and you would say, okay, those are the clusters. Of course, we can't see dark matter. We can only see baryonic matter and the galaxies and the stars within them and sometimes the dusty emission. So that's what we have to use to detect these overdensities of galaxies and learn about them. Okay, so I think hopefully I've convinced you, okay, these are interesting things to study. So the next question becomes, okay, how do we actually define a cluster or a protocluster, for that matter, so we can know what to look for? I'll give you a definition of a protocluster and I'll give you some alternatives. So a protocluster or cluster can be defined using the fact that they are virialized objects with a mass larger than 10 to the 14. You might ask, why 10 to the 14? Why not 10 to the 13 or 10 to the 15? Well, if you look at the dark matter halo mass function for different models here, so this is again lambda CDM cosmology, what you see here is this is sort of how many halos of a given mass you have. And what you see is this curve at around 10 to the 14, you see a break. So this essentially tells you that there are a lot more 10 to the 13 halos than there are 10 to the 14 halos, a lot more 10 to the 14 halos than 10 to the 15 halos. So it's a very good sort of cutoff point for these most massive rare objects.
That's at redshift 0.
At redshift 0, yes. So this is following the evolution, of course. When we go to the protoclusters, they will have lower halo masses because, of course, the halo masses grow over time. So this is about the clusters, I should say, at redshift 0, for example. Now, protoclusters are volumes then that will form in the end or collapse to form a cluster before redshift 0. This is very good in stuff like simulations because there you can track the dark matter halo masses over time and see how they evolve. It is not as useful observationally because, of course, we can't see dark matter, so we somehow need to estimate what the halo masses are at a given redshift. Now, it should also be noted that There are other ways you can detect clusters. It's not just by this definition. People discuss how you should define a cluster or a cluster. One other way, for example, is you can look at the intercluster medium. So what you have, what you can find is if you go into the X-ray and look, you can have detections of this hot intercluster medium. This is a detection in one of the able clusters at redshift 0.18. And you can see this sort of purple glow is the X-ray detection of this very hot 10 to the 8 Kelvin gas, which you find in the clusters. Another thing you can do is you can look at something called the red sequence. So if you remember before, I told you that there are very many of these red and dead galaxies. And this is an example of a color magnitude diagram for the coma cluster. And what you see is that this very well-defined relationship between the magnitude and the color with these galaxies. That's another way you could also try to see if you have a cluster. Okay. So observationally, we have to somehow estimate over time, or we have to estimate at different redshifts, what the halo mass is, the dark matter halo mass. Because then we can have some idea of, is this a structure that's going to grow into a cluster over time? How we do this is we essentially say that the more massive galaxies, trying to show about this cartoon, are expected to sit in more massive halos. Said another way, there is some sort of relationship between the stellar mass of the galaxies that we can measure or infer, and the halo mass of the protocluster. As an example, so you can see this is one of these curves. So this is done using something called abundance matching, where you take halo masses simulations and you look at the estimated stellar masses in surveys, and you order them. So you say the most massive stellar mass is rank ordered or sort of tied to the halo masses, the most massive halo masses. And you get this sort of relationship that evolves with redshift. And that is one way. There are more ways, but this is one way of estimating the halo masses. So for example, if you have something like a 10 to the 5th halo mass at redshift 4, you would expect it to grow into something like a Virgo or a coma cluster at present. And you can see this from some other simulation work that has been done. This is from Chang 2013, where he's taken multiple different, he's looked in simulations and found clusters in the simulations that have halo masses similar to something like a Fornax, a Virgo, a coma, and then trace them back in the simulations to see how they evolve over time. So you can sort of look at these numbers here and see that if you follow these curves up to redshift 0, that is how they would evolve. Okay. So now I've told you a bit about why the structures are interesting and how we could try to infer some of their properties to say if a protocluster is going to evolve into a cluster over time. So I want to give you sort of a general picture from simulations, or a picture from simulations, that sort of tells you how these structures, how we expect these structures to grow. What is the sort of the story of protoclusters as they evolve into becoming clusters? So generally we can put these in 3 phases. So one phase is sort of this core dominant phase very early. So while not a lot of the star formation happens in clusters today, if you go far back, especially above redshift 5, but even more so at like redshift 10, 50% of the star formation rate that happens in the universe happens in these protoclusters, and especially in the cores of these protoclusters. So what you have is a downsizing effect. So because the galaxies were in sort of the center of these primordial density fluctuations, what you have is they are evolving more rapidly than the environment around them, which means they form more stars quicker, for example. And this is why you see this sort of inside-out growth, where you have the growth of the core first, and then the growth of the individual parts of the protocluster later. The core here, just to show this cartoon, the core is this sort of red region by this red line, and then the total size of the protocluster here is this blue line. And you have the individual halos, kind of like I showed you before with the gray, and the galaxies within them. So between sort of redshift 10 to 5, this is what you have, this core dominated part of the story. And an example of this could be seen in some of the SPT protoclusters. So this is around redshift 4.8. This is sort of the transition where we become less core dominant, but I think it's a very good example of one of these. This is detected in sub-millimeter, and it's one of these heavily dust enshrouded protocluster cores, which are highly star forming. And you can see it kind of looks very similar to sort of the inner region you're seeing in this cartoon. Now, between redshift 5 and until about 1.51, what you have is an extended star formation phase. So here, and you can kind of see in these curves, which show the cosmic star formation rate density, both the total one, but also the one from the protocluster and the cores. You can see the cores start to become less dominant over time, because the outer parts of the protoclusters start to evolve their own halos start to grow and start to form stars. And so this is sort of the phase where most or a large part of the stellar mass of the final cluster will evolve. So about 65% of the final cluster mass evolves or sort of forms in this redshift space around 5 to 1. Then as you go to around, as I say, close to redshift 1.5, what you see is the transition starts where you're going from this extended star phase to sort of the final phase where the cluster is properly forming. This is why around redshift 1.5 you will start to see example of these sort of quiescent galaxies. This is shown here with the red points, and you will also start to see the formation of the intercluster medium, the hot gas we're talking about more so. And then from redshift 1.5, and then today you have sort of the final formation of the cluster where the core starts to become more dominant again, but it's not because it's forming more stars itself, it's incorporating the halos from sort of the outer skirts of the cluster and then incorporating them in, and this is how it grows. And this is how you end up, again, in Sauride manner, where the inner parts of the cluster falls in, and then the more outer parts, and outer parts, and outer parts. And this is how you end up, again, with the final cluster, where you have something like Virgo. So this is sort of the general picture we have of the evolution. But of course, an important part is a lot of this comes from simulation. So what we would like is snapshots across all of these different phases to see, can we see these different phases in the observations? And this is what we need to test this sort of theory. Okay. So now the issue becomes, we have some idea of how we can estimate or guess or have some evidence to say, is the protocluster going to evolve into a cluster over time, but we also need to find them. So there's a couple of ways of doing this. The issue we have is at high redshift, there are very few protoclusters, and their selection is very inhomogeneous because you have very different surveys with different depth and different instruments and so on. But generally, what you have is a couple of general methods that can be used to find protoclusters over densities. You can see an example here. So this is very good. This is prior to JWST, but it gives you a very good idea of how rare these substructures are. This is from Overseer 2019, and you can see a low redshift here. You have a bunch of different clusters that are detected with different methods. We're talking about the X-ray before, we're also talking about SPT. But then once you go to redshift 1.5, you have this transition between high redshift clusters and protoclusters, where you have some of the signs that we were talking about earlier, with stuff like an intercluster medium or red sequence maybe starting to form. But then once you go to high and high redshift, you see it becomes a lot rarer. And once you go beyond something like redshift 4 or 5, you only really have a handful of sources or a handful of structures. This has become slightly better with JWST now. We have maybe tens of these structures, but they're still very rare, especially once you go beyond redshift 5. So generally, what you do to find these structures are, one, you either use some sort of large, deep survey to search for densities of galaxies. Right? So again, the easiest way to say that there is some sort of protocluster is you just calculate density fields of your survey. You want a large survey, preferably, because that will reduce your cosmic variance. And you want a good estimate of the median or mean density field, right? So you can see how the protoclusters, they will be more over dense, they will pop up over the sort of mean or median density field you have, your background essentially. So that's one way of doing it. But of course, to get these deep surveys, you need a lot of data and it's very expensive. So another way people have found is there are certain types of galaxies which can be used as signposts to look for these protoclusters. This is galaxies in very red colors, sub-millimeter galaxies, kind of like the ones, if I go back here, the ones you see here with SPT. So these very dusty, dust-enshrouded galaxies, very heavily star-forming starbursts, because they are believed to be the progenitors in many cases of the brightest cluster galaxies that we see in clusters today. Another one is quasars, also has been tried to use. Interestingly enough, quasars themselves don't appear to be the best estimators, but a pair of quasars seems to be very good estimators of protoclusters. And there's a lot of discussion in the literature from them. So what I'm going to tell you about now is how to use the second method. So finding one of these signpost galaxies and then looking at the immediate environment around them to find out if they are in some sort of compact configuration or overdensity. Luckily, in this case, we actually can use both methods because the structure I will show you is in Cosmos, which is one of these large legacy fields. So in fact, we can do both here. They're not mutually exclusive. So we can compare sort of the larger scale overdensity and also the sort of compact configuration that it's in. Okay. So now I'll tell you about CGG-Z4, which stands for Compact Galaxy Group at Redshift 4. Very clever name. This was originally detected by SCUBA, which is a sublinear instrument. This is for what you see here. These contours are 3, 5, 7 sigma, and they are at 850 microns. So this is like dust emission. And the image in the background is Vista K-band. So this is 2.2 microns. So what you see is there's this very clear detection from the contours, but the issue is it's over a very large area. So what we can do is there's other instruments that can give us the dust emission on smaller scales to be able to determine which of the galaxies in the field are actually associated with this dust emission. So if we zoom in, this is a true color image. This is I, J, and K band. And then what you see here for the contours are ALMA. So ALMA allows us to go to smaller angular scales, better angular resolution, and sort of resolve out this very big SCUBA source to see whether or not there are multiple dusty sources within those contours. And what we find is there's actually two sources, both around redshift 4.3. So we call them, there's the big one here, which we call A, and then the smaller one to the side, which we call B. What's interesting about this is if you look at the other galaxies that we have in the field, so these, all these red circles here, also the ones over here, these are all the galaxies that we have with optical near photometry in Cosmos, around redshift 4 to 4.6. The photometrics redshift is around 4 to 4.6. So what we see is there's this sort of compact configurations of many galaxies around these dusty ALMA detections. And so this appears to be a compact galaxy group, interestingly enough. One thing we can also do is we not only have the dust continuums, this is dust continuum contours from 3 millimeter and 870, but we also have the spectrum. So this is how we determine the redshift of these two. And you can see multiple different lines here. So there's multiple CO transitions. This is 4 to 3 and 5 to 4. But we also have C1, which is very good for getting gas estimates in A, and in B we have something which is very rare, which is it's kind of faint, so it might be hard to see, but it's H2O in absorption. And H2O is, as far as I know, above redshift 3, we only have 3 detections of this so far, and it's an indicator that the galaxy is undergoing starburst, because to see this in absorption, you need a lot of star formation. And interestingly enough, as a side note, we didn't do this in the paper, but you can actually use this line as a way to estimate what the CMP temperature is at the redshift you're at, or you're observing. So what we can do is we can take the properties of these dusty galaxies and we can do SED fitting to tell us something about what their star formation rates are, for example, and their dust masses. So we combine all the different data here. The issue is a lot of these instruments, their beams are too large, as you saw before with the scuba data. So this star formation rate you're seeing here is the star formation rate of both the galaxies, both A and B, when we combine all their photometry. But what we can do is we can try to scale it. So I've scaled it here by the 870 from ALMA, where we have the resolution, and then we can compare with the 3mm to see if they agree for the two objects, and they agree fairly well, actually, which is nice to see. One thing that it doesn't agree is the radio, which is low for one of them. It's low for A, but that is not too surprising, since for these sort of fits, the radio is actually not fitted directly. It comes from a scaling relation which uses the far infrared submillimeter data here. So it's not too much of an issue. One thing we can do is we can also say something about qualitatively about the properties of these dusty galaxies. So what I've done here is I've taken the line ratios between the C1 and the CO43. And what this probes, and the x-axis, and what this probes is the total gas that you have. So C110 probes the total gas you have in your galaxy, whereas CO43 probes the dense gas. So in some sense, the gas available for star formation. There's an asterisk on that, we can discuss it if you want to know. But this will tell you something about essentially how much dense gas, if you have very low values, how much dense gas is available to form stars. So you would expect, if it's a dusty starburst, it would have very low values because it has a lot of cold gas available. And then on the y-axis, I'm showing the CO5 to 4 over CO4 to 3 ratio, which tells you something about the excitation state of the galaxy. Now, if you want the proper excitation, you would want the full CO ladder, so you want more transitions, but this is data we have available. This is the best we have currently. And what you see is, firstly, for our galaxies, which are the magenta ones, they appear to occupy a fairly unique part of the random space. So they have very low values compared to a lot of the literature sources we have, stuff like normal star-forming galaxies, other SMGs, and also these luminous infrared galaxies. And this shows you again that these are probably very dense, dusty starbursts. And they're also very close to the 1.56 thermalization limit when you're on the y-axis, which suggests that the gas is fully thermalized in this case. Okay. Another thing we can look at is the main sequence. So if you don't know, the galaxy main sequence is essentially, I was about to say something we stole from multistellar people, but it's a curve that shows you the sort of typical, for a given redshift and stellar mass, what's the typical sort of star formation rate you expect for a galaxy. If you're above the line, you're a starburst. If you're below, you're a quasar, not forming a lot of stars, as is compared to what is typical. What you see here is these are all the optical near detected galaxies in blue, and they appear to scatter around the main sequence, so they appear fairly normal. And then you have the ALMA detected ones up here, which are, again, appear to be way above. So they appear to be starbursts. Again, which is interesting and what you would expect in these sort of environments that we're in. Okay, another thing we can do is we can estimate the gas mass. So here I'm using the C1 line, and I've estimated the gas mass, and with the gas mass, you can get the depletion time. So the depletion time is essentially telling you if I have X amount of gas, and I have the star formation rate that I have, and it keeps being, the star formation rate steady, how much time will it take to use up all the gas? Now, this is sort of a simplified case, because that's not really what happens in actuality, but it gives you a good idea of how efficient is the galaxy of forming stars, right? There's something called a star formation efficiency, which is in fact the inverse of the depletion time scale. And what you see when you compare to a lot of the literature relationships, what you have is our sources have lower depletion times than what is expected. So that means they appear to be very efficient at forming stars. In fact, they're very close to some of the most star-forming proto clusters that we have, which is one of the SPT 234956, which is this structure which has 14 of these SMGs. This is one of the most star-forming. Its cumulative star formation rate is something like 10,000, more than 10,000. So it's one of the most extreme things. I mean, simulations have trouble reproducing these. And you can see our galaxies are actually very close, very similar to these structures, or these galaxies. So what is interesting about this is it could also suggest that there's perhaps an onset of quenching. If it's very efficient at forming stars, perhaps it suggests that in the future it will have used up its gas very quickly. And actually, given these depletion times, if you go to around redshift 3.6, there are evidence of structures, something called the cosmic vine, which has these massive galaxies that are quiescent, which seem to have had, given their star formation histories, a starburst within the last 500 megayears, triggered by some sort of merger. And this could be a candidate for when it's in that starbursting phase. Now, we don't know if a merger has happened for these structures because we don't have the morphology. Again, they're K-band dropouts, so we don't see anything. We don't see, if you go back to the image, let me show you quickly. If you go here, you can see there's nothing in these two. There's kind of something here, but this is actually a foreground galaxy, which means at any wavelength at 2.2 micron or below, we don't have any information. And that means that it's hard to say something about the morphology. So that's something where in the future, it would be good to have more data. Now, finally, I'll show off this estimate. So what you're seeing here is the halo mass on the y-axis and the redshift on the x-axis. And this shows you a bunch of different protocluster compact galaxy groups in the literature. You can see mine is here in the magenta, but you also have a lot of other structures across redshifts. And what this shows you is what the expected halo mass is. So if you remember, I told you that we could estimate the halo mass as the main progenitor, so of the halo merger tree. And then we can compare it to one of these curves for where we expect the structure to grow over time. So these two curves, one is for Fornax and the other one is for Coma. Virgo would be in the middle. And what you see here is our protocluster is somewhere in the middle. So most probably going to evolve into something Virgo-like. What you also have here is these lines which show the different sort of growth phases or way that the galaxies are growing. So below here, this is sort of the specific mass where you have shock heating. This region here is something called cold streams and hot medium, where you can have hot gas, but then you have cold streams of gas penetrate this hot medium. And this is how you can have the galaxies grow over time. And then at the end, on the other side here of the streamline, you have what is called hot accretion, where it's hot gas.
So room pressure would happen on the upper left?
Yes, yes, indeed.
Of the dashed or the dotted?
So these are different lines. So this is because in the literature, there's some debate. Right. So the original Deco line from 2006 is here, but there's been some, Emmanuel Daddy has done some work to say, well, maybe the line is actually not, it's not exactly like that. So there's still some debate on where the actual transition is. So this shows us essentially that given the halo mass we have, this appears to be a proper protocluster, right? It would evolve into something that is more than 10 to the 14 before redshift 0. Another thing we can also look at is we can compare simulations of the BCGs. So the expected BCG masses from simulations, and what we find is the masses of the two Dustron-shrouded SMGs in CGG set 4 are in the range that we would expect for a proto-BCG. So this also leads more credence to the fact that these are probably the proto-BCGs of an evolving protocol. Okay. So these are my conclusions. How much time do we have?
You're right on time.
Yeah, well, you can read them. Yeah, so I'm happy to take questions.
Great. Thank you. Great, so we're going to start with some questions from the students, then we'll have questions from everybody, and if anybody online wants to ask a question, please send it now, and I'll read it out at the end. Okay? Great, so any questions from the students? We don't have a lot of people who work on high redshift stuff, so there should be some questions.
Thanks, Malte, have you tried to use clustering harmony classify the clusters?
Come again?
Have you tried to use clustering harmonies? Some machine learning clustering harmonies?
So when you're thinking for calculating the open density?
classify, characterize the compact groups of the galaxies. Like,
So there's a couple of ways that you can do this. Typically, what you have for determining stuff like overdensities is you either do something like a nearest neighbor, or you do something like a kernel. So what I did was I typically work with something called a weighted adaptive kernel, which tries to estimate the typical sizes of these overdensities when selecting them. But yeah, I haven't personally done any sort of machine learning, but I know there are some attempts in the literature to try to do this for stuff like detecting overdensities and purposes.
I have a question about that plot where you show the star formation rates.
Stop when I'm there. This one or this one?
Yeah, that one.
Yeah.
I didn't understand what are the parameters in the axis.
Yeah. Okay. So if we go back to this, you can see the lines here, right? So what you have here is we can estimate. Oh, there's echo. We can estimate the fluxes. So what you're seeing here, this yellow marked regions, those are where the lines are. And we can get the fluxes for those lines. And then what we do is we take the ratio of the fluxes of those lines. So in this case, this is the flux for the C1 line, and this is the flux for the CO43 line. And the same here. So these are just the flux for the CO54 line over the flux of the CO43 line. That's what it's showing.
And in the next slide,
This one?
this one. How accurate are the measurements for the star formation ratio that they're showing?
Right. So the total star formation rate is probably pretty good. Because we have a lot, if you look at the SCP fitting, we have a lot of data here to also probably probe the peak of the dust emission. If you look, one snag here is, of course, as I told you, this value is the integrated one, so it's for both objects. So to get the star formation rate of the individual objects, what we have to do is we have to scale it by the resolved Elman flux. So there is some uncertainty in that. But again, if we look at the ALMA data, if you look at the scaled SED and look at the ALMA data, it seems to be fitting with what we would expect pretty well. So the fit is probably good in this case. So it's probably a good estimate. I think that's a bit more uncertain, which we can talk about, is the gas mass. So I didn't mention this because it's kind of quagmire, but there are many ways to get the gas mass. What we did is we used C1. What you have is you have what is called a alpha value, which gets you from your line flux to your gas mass. Typically, what you have in the literature is people use CO 1 to 0. And there's discussions on what the value of alpha CO is, for example. So you can see here, if you look at the legend here, you can see that for the SPT one, they use the value of 1. For GN20, which is another protocluster around the same redshift, they use different values per object. And there's also some people who've argued that the CO values are universal. Some say it's different. And another thing is also, if you don't have the 1 to 0 line, what you have to use is one of the higher transitions and then convert it to a 1 to 0 flux. So there are many uncertainties that come into this. So what I will say is, for example, with these is, especially for the ones that are more star forming here, or more star bursty, they might in fact not have the right alpha CO value. So they could actually be over here. It is possible that some of them are over there instead. And this is something that is difficult to do, and it becomes even more difficult to do with the high redshift, because you need a lot of time to observe something like CO 1 to 0.
Any more questions? Any more questions from anybody? Including online. I'm keeping an eye. If anyone wants to send a message. Oh yeah. Oh, here you go.
Thank you for the talk. I have actually like a trillion questions, so maybe I can do one and then yeah, and then maybe
1, 2.
something like that.
Yes.
Malte, I have a bunch of questions about protoclasses, like in general, and I would love to hear your thoughts on it. One of your last slides showed the growth of the mass scale exactly at that point. One thing that I always come back when I talk about protocluster is when stops being a protocluster from start being a cluster, right? And it's like maybe the main question for many people. Do you think that like dashed line that shows when ground pressure, for example, start being efficient would be a good way to split between protoclusters and clusters, or do you think that it's something else but split between them?
I mean, I think it is this is when the transition, I think, begins to start. I don't think it's a surprise if we go back all the way. I'm not going to do it, but if you go back all the way to the overseer plot, if you remember, the typical transition people have between what is a high set cluster and a protocluster is around 1.5, and this would be here. So it is on the other side of this line. But what I think happens here is because you're starting to have this hot accretion instead, I think this is probably where you start to see the transition really begin to the final phase. So I think this is definitely part of the puzzle. And of course, that's why I think it's important to really determine where the transition happens, but it's difficult to do.
Yeah, you want to follow up?
Did you want to ask a question, Jan?
Yes. In terms of imaging for morphology,
Yes.
so what is available? I mean, I thought this you don't have a JWST?
We sadly do not. So if you can imagine the Cosmos field here, Cosmos Web is in the middle, and this structure is down here. So it is outside of the region where we have JWST. But it would be very nice if we could get some JWST time and observe this. I've had some ideas about doing a proposal for next cycle where we go and ask for NearCam for this to try to get the morphology, because we know, even though these are heavily dust obstructed K-band profiles, we have seen other examples now with JWST where we're able to constrain, for example, stellar masses better and get morphologies because JWST is just so sensitive. So we can actually peer into to be beyond the dust and actually get some estimates. Another thing you could do, which I've also thought about, is near-spec view. So that would be another way to look at morphology as well.
More expensive.
It is more expensive, but you have stuff like ORCID, which has asked for, what is it, 5 to 10 hours per source. So maybe some of these are detected in NearCam, and again, we don't have NearCam, so we don't know if it would be detected in NearCam. I suspect it would, even though it's very dust obscure. But you have other SPT protocluster galaxies where with NearCam you could see them. But that would be another way of trying to.
And how many Redshift 4-ish clusters or cosmic clusters have James Webb data? Frame it that way.
Let me think. Off the top of my head.
Order of magnitude.
10. Maybe, yeah, 10.
And you can actually see morphology, like
yes.
You can say this is a disk, this is a merger, this is a.
Well, yes, in some of them, yes, not all of them, but in some of them you can. It becomes harder for the more extreme ones, right? Because they're more dust obscured. So even though we have detections, and we can use that with the SD fitting to constrain the stellar mass better, sort of in detail analysis of morphology becomes harder for us because it's still very highly dust obscured. But yeah, there are examples of protoclusters where this has been done. Yes. The Cosmic Binds one.
Last questions? Yeah, Diego, a couple more.
when you show the plot of the dilation time function of the how more are forming are than the main sequence, yes, that one. Do you expect of those some of those galaxies, like for example the BCGs of the protoclusters, to keep accreting gas
over time?
Yes.
Yeah, because they have to grow. I mean, in this phase, they are done growing in terms of their mass, right? So they could still very much still grow. It is still possible. One thing that's also important to think about is you can have rejuvenation later on. So when I talked about the comparison between this and later on the cosmic wine, which is poison, of course we're catching that structure, the cosmic wine, and those massive galaxies in a point of time where they are quiescent, they don't form a lot of stars, but of course that doesn't mean in the future you can't have rejuvenation.
Yes.
And that's probably what is going to happen. Because they haven't necessarily reached the sort of stellar masses you would expect of the galaxies that you find in clusters at redshift 0. So yeah, there's still possibility of more gas.
The follow-up with that is that I don't know if someone already has done it, probably they have, but most of the structures that could be considered protoclusters at redshift 3 or 4, for example, won't be protocluster clusters of redshift 0, right? Because some of them will merge.
They'll fail, essentially, yes.
Will split stuff.
Yes.
So, for example, many BCT candidates that you can observe at redshift 4 will end up suffer starvation and be accreted by other BCTs. Do you know if someone has quantified that, like the fraction of successful clusters from protoclusters?
To my knowledge, I haven't seen like a direct number of probability, and that's actually something I've been discussing with Rory a lot, because he's doing a lot of work now trying to find what the sort of using the different properties that we can observe, getting some sort of probability of saying, okay, if I say I'm an observer and I have some estimate of the halo mass, the overdensity, the stellar mass, blah blah blah, so on. If I take those, what is the probability that it's going to end up as a cluster?
Yeah.
So this is actually something that I think hasn't been touched upon a lot. What we're doing right now is very simple in a way that we get what typically happens with observers is, especially the high redshift, is we find some overdensity on the sky. We take the most massive galaxy in stellar mass, we calculate the halo mass, then we put it on this plot and say, oh look, it'll end up there. So that's essentially what a lot of us are doing. And I think it's missing a lot of the information that you can use to say how likely is it actually that it's going to end up there, right? So it's a lot of inductive reasoning, of course. We can't say for certain, but we want as much evidence as possible to say, okay, these are actually going to end up as a coma or Virgo or something like that, right? Because I agree with you that there is a probability that some of these, maybe they don't end up as a proper cluster, right? And we also note that in some cases, for something like a coma, the mass growth happened fairly recently in terms of time, right? It grew for a lot of time, if I remember correctly from simulation, stuff like Magneticum. Virgo was more massive for a very long time compared to coma, but then it is expected that very recently, sort of within, what is it, like, since redshift 0.5 or something, it overtook it. So, relatively recently, you know, I think in redshift, I always remember the redshift 1, that's half the age of the universe. Anyway, so I think, yes, to my knowledge, no. It's something that has not been studied as much as it probably should, or at least I would say the interface between the simulation work and the observation work is not all there yet. So I think this is something that can be improved.
Thank you.
Great. And if there's no more questions, including online, we will leave it there. Let's thank Malte one more time. Let's get some lunch.
Yes, I didn't get you so much.
Yeah, we never got there.
No.
You did cover a lot.
Yeah. But this one is very cool. This is some Alma data that we got last cycle. So we're trying to, you can see we had a bunch of different protoclusters, and this is including the one that I found. And the idea is essentially we can try to determine whether or not, if you remember the intercluster medium I told you about earlier, we can use ALMA, sort of large scale to short scale ALMA data, ALMA fluxes, to try to determine if these protoclusters have a circumgalactic medium, which is tied to the galaxies themselves, or a sort of a progenitor of the ICM, a proto-ICM, which is more tied to the properties of the halo of the cluster. This is something that we have almost all the data. We're missing two of these structures. We're missing this one and this one, mine. And once we have all the data, we can start doing the analysis.
That's very useful for people that do environmental studies like us.
Yeah.
Yeah, because it's already been done with this one. I think this is the extreme one I told you about. But it would be cool to see if there's some sort of relationship where evolution with either the internal or sort of cluster properties.
You should go with the podcast Católica Valparaíso as well. Have CGM and all that.
I've been talking to
Rafael.
Yeah.
Bueno, I think Rafael, Cristóbal, and Nicolás I'll have overlaps with you.
Yeah, definitely.
Try to get, if you want, I can tell them to invite you.
Yeah, for sure.
Sure.
They have a seminar program too, so we could just go and give the same talk to them.
Yeah. This is the
Are you going to check that the fraction of successful cluster one? Or?
Yes, we're actually just discussing.
Wait for me, I go to the bathroom.
Yeah, sure. Do you want to go to the bathroom or anything like that?
I just need to for this.
Yeah.
That's it.
Yeah, I think that's part of the goal. Try and connect what's happening on Brinch, find something like that. What's happening on Brinch.
Well, there was nothing, there's no question.
No, I think Lucia was there briefly, but she had to go early, so I think she probably would have asked a question.
Yeah, probably.
Yeah, I remember that there was something that we were discussing with Lucia as well, right? And you're going to link with Lucio.
Yes.
Well, I mean, you also show me the fundraise some of the things you can do, but it's not necessarily doesn't give you very strong or kind of
Yeah, so some indicators are not super strong predictors, but it doesn't mean that they don't add some additional constraints on strong. So
that's a good point.
That's why we want to try and combine multiple predictors into one, in the same way that Sean did for the emerging clusters.
And are you going to use a hydrogen like there's a magneticum or?
No, it's purely
I mean, there are first but in the future maybe.
I mean, yeah, could be done. Could be done. I'm not planning to do this. Yeah, I want to just use basically things that can be measured with each other. Actually, most of the things that we need can be measured with each other.
One thing that would be interesting, for example, if you had the full SEDs, is you could look at specific fluxes. So if you have something that is very bright and specific element, or has a very strong line detection, is it typical of, I guess, it's the protein BCG? That would be a good indication.
Yeah.
Yeah.
But even if we want to add like hydro parameters in later, we can, because this model can easily be adapted to just add more and more indicators.
Right.
So I think it's good to start with the simple ones from the simulation, and then we can include more into the same methodology.
Yes, I think it's, also because I think it's a lot clearer because these are the simple problems are the ones people are most likely to have.
Yeah.
Right. So we don't necessarily have to see one detect of your specific program.
Right. Yeah, I think maybe the mocking part is a bit where it gets more complicated. You actually want to turn scalar masses into, whatever wavelength that you're observing. That's where it gets a bit more complicated. Yeah, but I think it's interesting, and we also have star formation rates from into, which in some ways are kind of useful because they're tied to the abundance factor.
Right. So they're payment.
Yeah, painted on, but it means that there's also guaranteed that they have to have the right star formation rate to be able to get the right stellar mass in the right halo later.
Right.
And actually, that's not guaranteed in hydro simulations. So I think in some ways,
No, because they're not tied to it, I guess.
yeah. It's slightly more observationally constrained for the star formation rates of this like very simple painting on galaxies model. Yeah, but yeah.
No, wonderful.
So
Very
I think
interesting.
we can definitely like add more stuff later. But I'm going to start simple.
Yeah, no, for sure.
Yeah.
Well, and I can help in any way. Happy to.
Yeah, great.
Yeah, it sounds amazing.
We should do this project.
Yeah, for sure.
Yeah.
As a total Rory, I mean, if you do a code which is like you put in your parameters and it spits out a probability of this is going to end up as a cluster at the end, you will get a million citations. Every single proto cluster, especially the high ratio proto cluster person, will be like, yes, please.
But that's exactly what this model does.
Because it's been like this. I mean, I remember back when when I went and talked to the other Cosmos people about this, it's been like this forever, right? It is exactly this. You find your own density. You get the highest stellar mass, you get your halo mass, and then you look at the chunkers, and then you say, oh, look, it's going to be a Virgo or Coma. And you don't want it to be a 4-next because it's too low. You would rather it's Virgo or Coma. Yes, that's essentially what people do. As I said, there's slightly more now. You're starting to see people use the BCG mass more.
It's not a good predictor. I already checked. It's quite bad, actually.
If I remember correctly, Reyes de Remus also did this for magnetic home, and she also found no, the BCG mass doesn't really.
Quite poor. Yeah.
It is. It seemed, if I remember correctly, a lot of the estimators weren't the greatest, but the best one was just the overdensity.
Yeah.
It's the overdensity. Because it is essentially probing the feeding of galaxies and halos from the cosmic web. So it essentially is telling you the ability of the structure to grow. Which is something I should actually have mentioned this. I just forgot, but because we have the large scale information in Cosmos, we know this structure is also overdense and large. So this is also another sort of something that's indicative, but gives us some more credence to the fact that this is a real protocol that's going to grow. It's not only overdense on small scales, but also large scales. So that's something I've advocated for a long time, that you really want that large scale information, because I have a suspicion that some of the ones, especially the ones where you have some stuff, I've seen this as like AGN fields, where people say, oh look, there is an overdensity. And then it's like, yeah, but your field is like tiny. So I mean,
Just true.
Is it true?
Yeah, well, it depends how big you have to go, which volume you have to measure your number density in. And
this is actually something that I don't know, and I would love to. This is something that would be great to also test with like Moxa simulations. Is how large a field you actually have to probe to get the average of a median density field. So you know it's over dense process.
So we found that the 15 megaparsec was the best, but there's a range.
Right. And the size of the structure, right?
That's the volume in which you measure the number density.
Right. But the question is, I guess the question is slightly different, because you need to say why that much of how old it is.
No, sí, el tubo ahí. No, es que acá vino de no ver mi computador está diciendo. Es que acá vino el anuncio.
Thank you.